Hello, everyone. Today, we will continue discussing the uh, diode topics. And today, we will discuss the other types of diodes. So we discussed the power diode or the general purpose diode. And today, we will discuss some other diodes. We use it in industry. So this is going to be the topic and objective of today. Figure out other types of diodes and their applications. So let's start firstly with the solar cells. I think, guys, all of you are familiar with the photovoltaic or solar cells. So the solar cell is nothing but material or a type of diode that receives the light from the solar energy or the solar light. And based on this light, it will inject electrons inside the depletion region in order to allow to break the depletion region resistance and allow the electrons to start flowing and the electrical current to flow in the cell. So this is nothing but a diode. This is called solar diode or solar cell. And it's well known in industry by photovoltaic. Okay, so a solar cell is a PN junction with no voltage directly applied across the junction. So we do not apply volt because actually the source of energy is not going to be from the applied potential. The source of energy is going to be the light from the sun. The PN junction, which converts solar energy into electrical energy, is connected to a load. So once you connect this to a load, you will create a path for the current to flow, and this will allow to energize or supply power to the connected load. When light hits the space charge region, electrons and holes are generated. And once electrons and holes are generated, it will allow the electrical current to flow, as we discussed. So they are quickly separated and swept out of the space charge region, the depletion region, by electric field, thus creating a photo current. So the idea is, once you made free charges, these free charges will allow the current to flow. And we call it photocurrent. Why photocurrent? Because it's coming because of the photons, because of the light. So this is the idea of the solar cell. The generated photocurrent will produce a voltage across the load, which means the solar cell has supplied power to our connected load. So this is the concept, guys, of the solar cell. If you are familiar with the solar cell, you know the characteristic of a PV, guys, is something like that. This is the relation between voltage and the current. So this is current and this is volt. According to the amount or the intensity of the sunlight, you will have a value of current here, and this is going to be the volt of your diode, which is expected to be like from 0.6, 0.7, something like that. So this is a volt of one cell or one diode. And the current here depends on the light intensity. Okay, so we expect to have many characteristics of the photovoltaic like that. Depends on the amount of incident light on the diode itself. So this is called photovoltaic cells or solar cells. So this is one, let's say, very important source of energy in our life now. You can have some PV panels on the rooftop of your house, top of your house, to generate electricity, and you can consume this electricity in home or supply this electricity to the electrical grid, or let's say sell the power to grid. Okay, and this is actually very helpful in our life today to have what's called uncentralized power plants. So you can have your power plant, small power plant, in your home to generate electricity. Okay, so this is one interesting type of diode. We use it now in our life. As we discussed, the application of the solar cells, it can be supplying the electrons in satellite and space vehicles and some calculators. And this is very conventional, guys. So one of the well-known calculators type that can be working with solar cells, this I believe I can see that like maybe 30 years ago. It may be older than 30 years even. Okay. But this application is very old application. Also satellites, satellite, you don't have a source of power for satellite to be connected with. So the only way to supply satellites are the energy coming from the sun. So this is a very original way we use it for supplying satellites. Also supplying race cars in events or sun rays events. So this is also one of the applications. Supplying electric motors or charging battery back. We can say this is relatively or recent applications we have. And for sure, guys, these are the applications which are coming from the solar cells. So all of these applications will depend on using what's called PV panels. And the PV panel itself will consist of so many cells in order to generate this electricity. Okay. Later on, if you take the renewable energy courses, you will learn more about the photovoltaic. This is one of the interesting topics we have now in our electrical engineering classes. And it's required a lot actually in industry to know how to control the photovoltaic to achieve or to capture the maximum possible power from the photovoltaic. Okay, so this is what's called in industry MPPT or maximum power point tracking. So your PV panel will have a characteristic like that. This is I, this is V, and with voltage and current changing, you need to achieve the maximum power point, which is around this point. So with the different characteristics, how can you achieve this maximum power by controlling this point? So this is called the MPPT locus, which is going to make control for your PV panel to achieve the maximum possible power, whatever the incident light or the light intensity we have during the daylight time. So this is one interesting topic of the solar cells. We use it in our life today. One very important type of diode, guys, is called photodiode. What is the idea of the photodiode? So the concept of the photodiode is it's actually the opposite of the solar cell. So instead of getting light from the diode in order to generate electricity or allow a diode to on, we have the opposite here. We have a diode depends on some photons come on it in order to connect, not generating power. So let's see this type of diode together, guys. So photodetectors are devices, so we call it photodetector, devices that convert optical signals, some optical lights, into electrical signals. So still will convert optical to electrical, but it's not a source of power. It's not going to generate power. This is a different application or different technology. An example of the photodiode, guys, which is similar to solar cell, except that the PN junction is operated with reverse biased volts. So technical wise, it's going to work based on the reverse biased volt. So if you have a source of light like LED, and LED is one of the lights as well, so what will happen? This light or photons will be applied to the photodiode, and when you apply this to a photodiode, it will send electrical signal. What the benefits? What the benefit of using this? Why we didn't use the signal immediately from here to be supplied to the output? Because by the end, I applied a certain signal with a certain amount of current, let's say several milliampere, whatever the value, and voltage magnitude. So we have a pulse of a certain voltage and the current here. And by the end, we'll have also a source, or the output here is going to be several milliamperes and voltages as well. What's the benefit of using this now, since the output signal and input signal can be like compared together or very close in terms of values? So the benefit is to have isolation. Isolation means the negative here, this ground, let's say this is ground number 1, is different to that ground. This is ground number 2. So we achieved here the isolation. We call it, guys, the galvanic isolation. And this isolation can reach to relatively high values, like 5 kilovolt, for instance, like 6 kilovolt. So you can find some ICs in industry now with these values. And the benefit is, with isolation, whatever happening in the input side here, disturbance or whatever, will not be objected to the other side, which means if you have short circuit in the input here, so this is not going to damage the circuit in the output side. The optocoupler itself will be defected or damaged, but this to protect your output circuits. For instance, guys, if you have microcontroller generating pulses for relatively high power circuits, so I'm going to say here you have some high power circuits. So this high power circuit, guys, can be some power electronic switches, and these power electronic switches will have 3 terminals, 1 terminal for the gate and 2 terminals for the power. So the gate terminal can be connected to the output here with relatively low volt, like let's say 15 volt, for instance. But the transistor itself or the power switch itself can support maybe like 1700 volt, and the current can reach to hundreds of amperes. So in hundreds of amperes. And this is relatively high power compared to the microcontroller. So the benefit is whatever happening in the high power side here will not defecting the microcontroller sides. So if you have something like short circuit or anything in the power circuit here, you will protect your power circuit by any type of protection, but at the same time, we don't need our microcontroller to be burned. So the operation depends on this optocoupler will be broken in order to avoid breaking or damaging the digital controllers used. So this diode or photodiode, or let's say it's the technical name of this photodiode along with the LED is called optocoupler. So in this case, it will prevent damaging the other side of devices. So this is one important application. We use it for photodiodes. Here are the different applications I just mentioned. So photodetectors to detect the photons or light, measuring light intensity. In some applications, guys, in electrical system utilizations, we need to measure the light in places in order to be sure the light is distributed in the place as required, as desired in our design. So we have a meter called lux meter. So lux is a unit to measure the light intensity in a place. So lux meter is a device that uses the photodiodes in order to indicate how much light we have in a certain elevation in a certain indoor place. So this is called lux meter. Another application is optocoupler or optoisolator. So this is the one I just mentioned in the previous slide. And in this case, a LED is used as a source of light, and the photodiode is used to translate the pulse to the secondary side of the optocoupler or the optoisolator. And the function again is to have isolation between primary and secondary or input and output. Also remote controls. All of you know remote controls. So remote controls are the same idea. So for the remote control, you send a signal, optical signal, and this is from a transmitter, and a receiver is our photodiode, which will translate this signal in order to turn on or turn off a certain device. So this is remote control also. Okay, so these are some applications for the photodiodes. Let's compare between LDR and photodiode. So the difference between photodiode and LDR, guys, so this is a comparison here between the LDR and photodiode. LDR, guys, is called light-dependent resistor. Light-dependent resistor. So the light-dependent resistor is a resistance that will change its value according to the incident light on it. So let's introduce this to you here. So everything is written in the comparison. Firstly, the definition of the photodiode, we already understand now the photodiode, but let's read the definition here according to this comparison. So photodiode is a it's PN, not PIN, PN junction semiconductor diode, which can convert the light energy into electrical energy. Okay. But the light-dependent resistor is a light-dependent resistor, or the light-dependent resistor is a passive circuit component. Passive, guys, the word passive for electrical elements are referred to resistor, inductor, capacitor. So these are called the passive elements. Active elements have electronic components. So we can consider diode as active element. So we have now passive and active. The passive are the RL and C elements, and the active depends on the semiconductor material, diode, transistor, whatever the device. So Apparently, we can say both of them can do the same function. But what is the benefit or what the difference? So let's go more in deep to see here. Firstly, the biasing. Biasing means how to operate. So the photodiode is mainly designed to operate in reverse bias condition. So this is working in reverse bias. But LDR are mostly used forward bias condition. The device resistance, the photodiode acts as unidirectional resistance because the current can flow only in one direction. But in LDR act as bidirectional resistance because the current can flow in both of directions because it has no electronic component inside. It's just resistor. Regarding the material used to create the photodiode and LDR, so the material used for manufacturing a typical photodiode are like any semiconductor material, like silicon, germanium, indium gallium arsenide, silicon carbide, all of these types of semiconductor material, either intrinsic or extrinsic type. But for the LDR is made of cadmium sulfide. So this is the difference between the materials. Regarding the response time of photodiode is relatively less than that of LDR, which makes it comparatively faster. Why? Because by the end, it depends on the flow of electrons in the p-n junction, and this is relatively fast. So in these applications, guys, or for such type of diodes, we have what's called slew rate. Slew rate means how much voltage per second can be flow in the signal. Or let's say sometimes we say volt per microsecond. So it can reach to kilovolts per microseconds. Okay, so which means this is very fast. This is called slew rate. Okay, but regarding the response of LDR, so the response time of LDR is more means it's slower, so it takes more time, which makes it quite slow. So if you need fast response, so LDR is not the perfect selection, but the photodiode is much better in this case. The applications, photodiodes are widely used in light meters, as we mentioned, like lux meter, automatic shutter controls, smoke detectors, remote controls, optocouplers, solar cell panels, exact measurement of light intensity in scientific experiments and instrument and industries. So it's preferred in many industrial applications. For an LDR, guys, it's mainly used as a light sensor. So the main application for LDR is the light sensor. Some other application of LDR are in street light design. So we use it in a street light, guys, in order to turn on or turn off the street lights if the daylight started. So we need to turn off the street lights. So LDR is mainly used in this type of application. So this is a quick comparison between LDR and photodiode. Let's see another type of diode, guys, which is LED or light emitted diode. So the light emitted diode now, the function is the opposite of the optodiode or optical diode. What's happening in LDR? Sorry, in LED. So the light emitted diode or LED converts current to light. So in the photodiode, light is converted to current, but here current is converted to light. The semiconductor used in LED is called direct band gap material. Like what? Like gallium arsenide, okay? And the electrons or the electron and the hole can recombine with no change in momentum, and photons or light wave can be emitted. So once you apply your volt across this device, what happens is it can flow the electrons and allow a current to flow. This is in what's called direct band gap material. What about indirect band gap material? Like in silicon. So conversely, in indirect band gap material such as silicon, when an electron and hole recombine, both energy and momentum must be conserved so that the emission of photons is very unlikely. So the idea here is the material itself, if it is direct band gap material, so it can combine and generate photons or light. So it's not the indirect band gap or like the silicon one. So it has special material, which is direct band gap material. LEDs are fabricated from gallium arsenide or other compound semiconductor material, but not the indirect band gap materials. And LED, the output light intensity is also proportional to the diode current, which means the light intensity depends on how much current is applied to your LED. So this means you can control the light of LED by means of how much current is injected in the LED. Okay. Regarding the LED, guys, LED are fabricated for numeric and alphanumeric displays. So these are some applications such as readout of digital voltmeters. So we use it in digital voltmeters. You know, all of you know the digital voltmeters, we use it in our labs. Also, it's used in lights and TV screens. Now, the LED is preferred in terms of light because it consumes very less power compared to the conventional light sources. So you can get the same amount of light like the conventional bulbs, but with very minimal power consumption. So we do prefer LED lights because it's consuming very less power compared to the conventional lights. And the same is also for screens. So TV screens now, you know, it became very light and consuming less power compared to conventional TV screens because it's made of LED. Also, LED may be integrated into optical cavity to produce current photon output with a very narrow bandwidth. This is very important, guys. So the LED light is or has very narrow bandwidth, which means it can be concentrated and move for longer length compared to conventional light sources. Okay. Such a device is a laser guide, which is used in optical communication applications. So once you have, guys, narrow bandwidth, so this means you can move this light for long length, long distances. Okay, so for that, we use it in laser applications. Also, the LED can be used in conjunction with the photodiode to create an optical transmission system, and we already discussed one part of this in the optocoupler. So the idea is you will have a certain input signal to your LED, but in order to control the light intensity of a LED, you need to have electronic circuit to control this current. We call it drive circuit. So this drive circuit is going to control the current of our LED in order to control the light intensity of the output signal. And now we can use the output optical fiber can be transmitted now from the transmitter, which is the source of light, to the receiver, which will receive the light by means of photodiodes and then use amplifier in order to get the signal back again. So this is one interesting applications also of the LED. So LED along with the photodiode can be used for the optical fiber signal transmission. And it's used a lot also in our life today. So for the time being, guys, we discussed the solar cell, the photodiode, the LED. So these are three special diodes. It's not general purpose diodes. Now, we have another type of diode called Schottky diode. So what is Schottky diode and where we use it and why we use it? So let's see together here. Firstly, we have two important differences between the regular or general purpose diode and the Schottky diode. The first thing is the switching time from forward bias to reverse bias is very short, which means it's very fast diode. Okay, so this is the first difference. It's very fast diode. The second difference is reverse saturation current for Schottky diode is larger than that of a PN junction diode for comparable device area. So it has larger reverse current compared to general purpose diode. So this is the second difference. If you would like to compare the forward characteristic, so if this is, for instance, a PN junction diode, it turns on at a certain turn on V gamma here. For the Schottky diode, as you can see, it turns on at less voltage magnitude, and this makes this diode faster than the conventional, or let's say the traditional or general purpose diode. So in any high frequency application or fast pulse width modulation application, we do prefer to use Schottky diodes instead of general purpose diode. But if you are going to use your diode, for instance, in rectifier circuit, so you know rectifier circuit is converting AC into DC. This is the rectifier. And you know that the frequency of our AC signal is 60 hertz. So it's not that fast. So we can use regular PN junction diode and rectifiers. But in other circuits, if you have relatively high frequency, like in fast PWM circuits, you may have PWM circuits in from several kilohertz to several hundreds of megahertz. So in this case, we have to use Schottky diode, not the general purpose diode. So this is one important thing regarding the Schottky diode compared to the general purpose diode. Here, guys, this is a numerical example to show the differences between the Schottky diode and the other diodes. So in this example, we need to determine the diode volt. So in this example, we have the reverse saturation current of a PN junction diode and the Schottky diode are 10 to power minus 12 and 10 to power minus 8. So the PN junction diode is 10 to power minus 12 and the Schottky diode is 10 to power minus 8. So as you can see, the saturation current of the Schottky diode is relatively high compared to the conventional, or let's say the traditional general purpose diode. What do we need here? Determine the forward bias volt required to produce 1 milliampere in each diode. So since this is the saturation current, how much volt we need in order to allow 1 milliampere current to flow in our diode? So this is the question now. It's direct substitution in our relation. So this is the relation of current, of the diode current, you know, ID. The diode current equals saturation current times e to power Vd over Vt. So now we have the ID, which is the required diode current. We have Is, and Vt is constant, and we need to know what is the Vd. So let's take the logarithm for the both of sides in order to get the Vd in the exponential here in order to get this value. So we can say now Vd equals Vt ln Id over Is. Substituting the relation now with the two different values, you know, for Vt is constant at the room temperature. So assume that is the Vt at the room temperature. So we have 0.026 volt times ln the drain, the diode current is 1 milliampere, so 1 to power minus 10 to power minus 3, divide the saturation current of the general purpose diode, 10 to power minus 12. So this requires here 0.539 volt in order to allow 1 milliampere to flow. If you consider the Schottky diode here, guys, so substitute with the saturation current here, 10 to power minus 8. So we need only 0.299 volt to have 1 milliampere current. So this is the difference now, guys. So the voltage required to initiate 1 milliampere current in the Schottky diode is less than the volt required for the traditional diode. So this is just to show you guys a comparison between the two diodes, what happens if we need to have a certain current in the anode to cathode circuit or the diode current. Another type of diode, guys, is called Zener diode. Actually, we use Zener diode a lot in our life today, especially for the protection. So let's see what the Zener diode and what the difference between Zener diode and the general purpose diode. So firstly, Zener diode is heavily doped semiconductor device that is designed to operate in the reverse direction. So this is the difference, guys. Since the material is heavily doped material, so this will allow this material to work safely here in this reverse biased region without damaging. So the general purpose diode, if the volt reaches the value of the breakdown volt, what happens is the diode is gonna be burned or damaged and cannot be used anymore. But for the Zener diode, since it's high or heavily doped semiconductor material, so it can work in the reverse bias region here. What's the meaning of working in the reverse bias region? It means if the volt reaches the value of V Zener, in this case, as you can see, the volt is saturated, the volt will be constant, and current is gonna increase like that. So you have relatively high current flowing in your Zener diode now, but the volt is gonna be saturated. Since the volt is gonna be saturated here, guys, so this can be used actually to saturate or fix the volt at a certain value in our circuit. So it could be used now in protection applications. So this is the concept of using the Zener diode. Let's go more in deep here and read the details of this diode here. So when a reverse voltage is applied to the Zener voltage, a small reverse saturation current will flow. This is in this region, guys, during this period, in a small voltage magnitude. As the reverse volt increase, the reverse current increase drastically and sharply, but this at the value of the Zener volt, the value of the Zener volt. We're not going to say breakdown volt anymore now for Zener because it's not going to be like breakdown, but the expression, the right expression for a Zener diode is going to be the Zener volt. So instead of the breakdown in the regular diodes, we do prefer to say Zener volt, okay? It's the same magnitude, but I do prefer to say Zener volt because the diode is not going to be breakdown like the other general purpose diodes, okay? So again, since we can use this to fix the volt or keep the volt constant in circuits, so we can use it now, guys, to regulate the power supply volt. So regulate the supply volt means keep the voltage constant. So this is one of the most important applications for a Zener diode, which is power supplies. We can use it in power supplies. So it's used to regulate the volt in DC power supplies in light current, if the current is relatively low, not very high current. And we will see together in this class, guys, how can we design a power supply for low current and high current for both. But preliminary now, we got it that if the current is low in a power supply, Zener diode is fine. How low? We need to make some numerical description for this part in order to sense how much current we can use in a power supply with a Zener diode. So let's see this example together, guys, here. So in this example here, the objective is consider a simple constant voltage reference circuit and design the value of resistance required to limit the current in this circuit. This expression, you will hear it a lot in your life in industry, which is reference volt or constant voltage reference. So we need to have constant voltage reference in a lot of applications. Now, assume you have a certain circuit and you need to control the voltage across this circuit. How can I control the volt? If I need a constant reference, for instance, I need the volt to be constant at 5 volt. So I should sense the device volt and compare it to a certain reference. If the volt is higher than the reference, I should make a certain action. If the volt is lower than the reference, I should do the opposite action. But where is the reference? Where can I get the reference? The reference can be obtained from a Zener diode. So this is the benefit of having a reference or constant voltage reference in our life. So let's see how can we make sizing for the circuit of the Zener diode in order to be used as a reference volt. So the example says here, consider the circuit shown in figure. This is our figure. Assume that the Zener diode breakdown volt, which is the Zener volt, is 5.6 volts. So this is a volt of our Zener. And the Zener resistance is 0. Zener resistance is 0, guys, means it's ideal case. If we go back one slide again, the slope of this line here in the reverse biasing is 1 over R. You know, because I is in the vertical axis, V in the horizontal axis, so the slope here is 1 over R. So if we assume ideal case, which means this is right angle, so in this case, the slope is going to be infinity, and this means R equals 0. So the ideal case is R equals 0. And in this case, guys, we will consider VZ as, or Zener volt as constant, whatever the current value we have in our circuit. So this is the ideal case. The current in the diode is to be limited to 3 milliampere. So the current in our Zener diode need to be limited to 3 milliamperes. According to what? Should we limit the current of the Zener diode? Actually, it's according to the data sheet. So you will have a certain current you need to limit. We need to limit the current in the Zener diode here to 3 milliamperes. Okay, let's see how can we size this circuit. Sizing the circuit means now, guys, what the value of the resistor here? How much resistance we should have here in order to limit the current of this circuit to the value of 3 milliamperes. Actually, circuit-wise, this is very simple circuit. So we have now the diode voltage here, which is required to be 5.6. We have the supply voltage here is given 10 volt. So we need the current to be limited to 3 milliamperes. So simply we can say supply volt minus V Zener divide current equals the value of the resistance. Just apply Kirchhoff voltage law here in this circuit. So R equals V power supply minus VZ divide I. So 10 volt minus the Zener volt, which is 5.6, divide 3 milliampere. So the value of the resistance is going to be 1.47 kilo ohms. So this means if we add a resistance of 1.47, the current will be limited to 3 milliamperes in this Zener diode. Also, it's required here, guys, to know the dissipated power on this diode. How much power loss we have on this diode. This is very important also. So since we have 3 milliampere current flowing here, and the volt across the diode is 5.6, so the power loss across the Zener diode is going to be I times V. So 3 milliampere times 5.6 volt, which is 16.8 milliwatt. So this is the power dissipation across this Zener diode. Okay, guys. So this is a simple example just to see how can we size the resistance of this circuit to limit the current to the 3 milliampere in the diode circuit. So now, guys, in this circuit, we can use now this circuit like that, and the output here is going to be 5.6 ampere, or sorry, 5.6 volt all of the time. So this means we can use it now as a voltage reference. We can use this now as a voltage reference in a circuit or in a power supply. Okay. Now, this is a class activity. It's going to be assigned to you. I'm going to post that on eCampus. So for the previous example we calculated here, guys, you need to calculate the diode losses if the same circuit is used to supply a resistive load of 10 ohms. So instead of solving in the class on papers, you need to solve this on a paper and submit it on eCampus. So the question says now, if I'm going to supply a load, a resistive load of 10 ohms, so I will have a resistive load of 10 ohms like that, and I need to use the same circuit we have here. The Zener diode is here, and you know this is 5.6 volt, and we will have a resistance here, and this is our main power supply here, which is 10 volt. So calculate the diode loss if the same circuit is used to supply a resistive load of 10 ohms. Is it going to be different or not? So we have 10 ohms here. We have a resistance here. This resistance, we calculated the resistance, it's 1.47 kilo ohm, and we need to calculate the losses. I'm going to add one more thing, guys. So calculate the diode loss and also calculate the resistance power. So you have 1.47 kilo ohm resistor. I'd like to know also the power across this resistor. This is a focal point in designing power supplies, guys. So we need to know what the power needed here for this resistor as well. So please, I will make it on eCampus. So this it's not like a homework now. This is like quick assignment. So I'm expecting to have it by the next class time on Tuesday. So I will make the due date on Tuesday. So please turn the assignment as soon as you can. Okay. Now, we covered now, guys, the different types of diodes today. So we discussed the LED, we discussed the photodiodes, we discussed the solar cell diode, we discussed the Schottky diode, we discussed the Zener diode. So these are the different types of diode we discussed today, and we discussed the application of every one. We discussed also how to design Zener diode circuits for power supply application. So power supply application means we have a reference volt, so we know how to make a reference volt now. And with the assignment you have, you will know more about the sizing of the resistance, and this is going to help you to understand how to size or use Zener diode for power supplies. So this is a summary for what we discussed today. I'm just reminding you guys, the next lab on Monday, there will be a pre-lab assignment. I will post that on eCampus. Please build the circuit on the PSpice before of coming to our lab. This is gonna save a lot of time during our lab and will allow us to investigate the performance of our circuits inside the lab. Prepare yourself, guys. You have to have your computer with installed PSpice on it. You will share your screen with me in the lab time to show me the response of your circuits and the simulation results during our lab time. Thank you so much and have a nice weekend.